Hello, chemistry. This is the pre-lab activity that goes along with Lab 34. It's our last lab test for the year. It's titled Solubility and Thermodynamics. All right, so this is a pre-lab activity that goes along with Lab 34. The chemical for our pre-lab activity is going to be magnesium hydroxide. You can see the formula here. All right, this is a bottle of magnesium hydroxide. It has a common name, milk of magnesia. Some people buy this and take it for upset stomach. It is a basic compound, right, that is not very soluble. Let's go ahead and take a look at it, and you will see it's not very soluble. All right, comes out. All right, there we go. All right, it looks like a really thick, milky compound, and you can definitely tell that it's not very soluble, right? Okay, so our goal for our pre-lab activity will be to determine the KSP of magnesium hydroxide. We're going to do it very simply first by using our pH probe, and then you guys are going to do it in a much more complicated way when you actually do the lab. There'll be a titration and a little bit more detail to it, right? But this is really easy what we're going to do right now. All right, the first thing I'm going to show you is what a few drops of phenolphthalein to magnesium hydroxide do. All right, you can see it turns a nice bright pink color like that. That's showing you that there are some hydroxides in solution here, right? Even though it doesn't appear to be soluble, it is a little bit because we can see the hydroxides right here. So the next thing I'm going to do is I'm going to pour this into our test tube here like this. It's very viscous. See that? Right? It looks kind of like Pepto or something like that, right? All right, and so there we go. We've got our magnesium hydroxide with the pH indicator in our test tube. And so the only step to this pre-lab activity is to determine what the pH of this solution is. Here, it doesn't look like much of a solution, but we can definitely see there are hydroxides in here. So we're going to stick this pH probe in. We've got our pH meter going here. We're going to just give it a few minutes. You can see, I hope, that we're a little bit above 10. All right, guys, it seems like it's pretty much at equilibrium here at about 10.49. It's not changing very much. Oh, there it goes. Change to 10.5. We'll use that. If it is changing at all right now, it's changing very, very slowly. Okay, so take my pH probe out. Let it get rinsed off here in our fresh rinse water. All right, and we're going to do the math that goes along. And we're at 10.5 for our pH. Okay. We go ahead and take our calculator, subtract that from 14, and we get 3.5 for our pOH. Right, then we're going to raise this to a base of 10, so negative 3.5 to a base of 10. And we get our hydroxide concentration of 3.16 times 10 to the negative fourth. All right. Now the only other thing we need to finish this off is our magnesium concentration. Hopefully you see here that there are 2 hydroxides produced for every magnesium that's in solution. All right. So what that means is that this should be half of this. Right here is the ratio. 2 OH minus per 1 magnesium 2 plus like this, right? And so we're just going to divide it by 2 to get the concentration of magnesium, 1.58 times 10 to the negative fourth. Right? Now we have the concentration of our 2 ions that are in solution. There they are, right? And we're just going to plug them in here, right, for our KSP expression. You can see down here below, I've solved the KSP expression in terms of molar solubility with X, right? That's just to remind you that when we do this, make sure you plug in the 2X here and all that, but we don't actually need that because we know what X is. So you can see here, I've plugged in my magnesium concentration and my hydroxide concentration here. We're going to go ahead and plug it into our calculator and solve, and we get this, 1.58 times 10 to the negative 11. That's what we calculate. And the accepted value for the KSP is equal to 1.8 times 10 to the negative 11. So we're pretty close to the right answer here, just from measuring the pH of our milk of magnesia. Right, so what you're going to do in the lab is to do the same thing we just did, but you're going to use titration, and the chemical that you'll use will be calcium hydroxide. All right, AP Chemistry, so this is the lab video that goes along with part 1 of Lab 34, Solubility and Thermodynamics. All right, so for this lab, it's going to be very similar to what you saw in the pre-lab activity, where we're going to be determining the OH concentration, and this time it's going to be of calcium hydroxide instead of magnesium hydroxide, and instead of using the pH probe, we're going to perform a titration experiment to figure out how many OH ions are in our solution. All right, so before we begin, let's just take a look here at the temperature of our solution. All right, temperature of this solution right here is 21.7, right, is the temperature of our solution here. You should write that down. It's going to be important. Now, before we begin, we don't want any solid calcium hydroxide floating around. You can see this is a saturated solution. So what we're going to do is we're actually going to filter it out. All right. I'm going to filter this. We need about 10 milliliters of filtered calcium hydroxide. It's still going to be saturated because the OH ions can pass through the filter, but the solid cannot, right? And so it's not going to decrease in concentration or anything. We're going to have our saturated solution down here in just a second. So while this is filtering, let's talk a little bit about the math that you guys are going to need to do to finish this lab. All right. Our acid we're going to use to titrate, it's been loaded into our burette. It's 0.01 molar HCl. So that's the concentration of the acid. And once we get our base down below here, we're going to add it until we reach the neutralization point, right? So we need to record the volume of HCl that takes in order to calculate the moles of HCl that are required to neutralize this solution here. And since we'll be at the equivalence point or the end point, these two numbers will be the same. We can use the volume of base that we'll start with, which is 0.01, right, to come up with our OH concentration here, and from there it'll be very similar to what we did with the pre-lab, where we determined the KSP value by knowing what that OH concentration was. All right, so it looks like we've probably got about 10 milliliters here. Let's go ahead and see. We're going to use our graduated cylinder here to measure precisely 10 milliliters. All right, so we got 10 milliliters here. And I'm going to pour it into our Erlenmeyer flask that we're going to use for our titration experiment. And then we're going to use a rinse of distilled water to make sure that we get all the calcium hydroxide out. There's one rinse, and two rinse. And so you might ask, are we ruining the experiment by adding more distilled water? And the answer to that is no, of course, we're not. Right? The purpose of the rinse is to make sure we get every single mole of OH ion out of here, right? And the important volume number is already written down for you. It's 0.01 liters or 10 milliliters, and that was our volume of saturated solution. So, all right, good. We've got our solution of OH ions here, and we can show that it's OH by taking some bromothiol blue. 1, 2, 3, 4, 5, like 5 drops or so. Let's roll around and we can see that nice blue color there. That's showing us that we've got hydroxide ions in solution. That's the color that bromothiol blue turns in a base, right? So we're going to put it under here. We're going to start adding our acid and watch the color change. Before we do that though, we've got to go ahead and take a look at the volume that this burette reads. And I'm reading 3.2 milliliters. All right, we're starting out at 3.2 milliliters. We'll see what we get to, and that will tell us the total volume change here in the burette. Okay, so let's go ahead and get started. Do this really slowly. We want a constant stream of drips not too fast. There we go. So it's going to take a while here as we add our acid to our base. We're watching for the color change from blue to yellow, which is the color that bromothiol blue shows in base. All right, we're about halfway there. We're about 14 milliliters. Let's see how much longer it takes. It still is looking blue. No color change yet. Remember, we're waiting for this to change from blue to green, right? Or blue to yellow. We're watching for the color change. That means we've neutralized the solution. All right, we're getting pretty close here. We're about 22. All right, getting close. We should see the color change here in just a few seconds. And we'll shut it off and read the Buret rating. All right, it's probably going to change here really quick. Now, there we go. All right, so we changed from blue to yellow there. We're at the end point of our titration. All right, we went from 3.2 milliliters, right up here, all the way down to what looks to me like 27.15. 27.15 is what it looks like to me. All right, so we're just going to quickly subtract these two numbers and get our total volume of HCl that we use. So 3.2 minus 27.15, and we get this, 23.95, right? And then we're going to turn it though into liters, right? Because we don't want milliliters. So we're going to go 0.02395, right? And we're going to multiply that, 0.02395 times our 0.01, which will give us our number of moles here of 2.4 times 10 to the minus 4th. And since we're at the equivalence point right now, that's also the number of moles of this. Right? And then we can use this right here to come up, the volume of OH that we started with, to come up with the actual concentration. And we get this here, 0.0024 molarity. That is the molarity of the OH that was in the saturated solution. So you can use this to come up with the KSP of calcium hydroxide. This is the second part of our lab here, where we're going to do a temperature dependent measurement on this now. All right. So this will be in order to calculate delta H and delta S. So this has been boiling here for a little while, right? So it's really hot. And we're going to do this experiment again, but we're going to make sure we do it while the solution is hot. So it's very important to filter this quickly, right? And collect your 10 milliliters that you know the temperature of, and do it like that. Okay, so I'm going to have to do this very fast. Just bear with me here. All right. I'm going to get like kind of the maximum temperature reading here from this. And I'm going to filter 10 milliliters as quickly as I can. Remember, this is cooling the whole time. All right, so to me, it looks like I'm getting 97.1. All right, it looks like I'm at about 96.5. Let's filter it quickly. 96.5. All right, we're looking for about 10 milliliters. All right, so we're going to get as close to 10 milliliters as we possibly can. Right, and then we're going to let it cool. So we're letting it go here. We only want that 10 milliliters. We want the temperature to be as close as possible to that 96.5. And remember, it's cooling the whole time as it comes down through here. Okay, so we're almost to 10. As soon as we get between about 10 and 20, I'm going to pull that off because this is cooling the whole time. And as it cools, right, the equilibrium is kind of shifting here. So we want our hot calcium hydroxide as much as possible. All right, we're going to get a little bit more than about 10 milliliters, and then we're going to let it cool back to room temperature before we begin the experiment, because as long as there's no solid remaining here, we're going to have the same amount of calcium hydroxide in solution that we had at 96.5, because equilibrium can't be established if we don't have solid there waiting for us, right? And we're a little bit above 10 right now. I'm going to go ahead, I think, and pull it off. We're going to put this beaker down here. All right, we've got our 10 milliliters right here. It's definitely not at 96.5 degrees anymore. It's a little cooler as it's gone through, right? But it is still warm, right? And hopefully, we didn't give it enough time to come to equilibrium. So we're going to just kind of let this cool off and perform our experiment once it's cool. All right, I'm going to move this out of the way for us. We don't need this any longer. All right, this has been sitting here. It's now at 89. It's now at, let's see. So this has been sitting here for a while cooling as well, and it's only at 92 or 91 maybe degrees. So we've cooled a couple of degrees from our 96.5, but we're still going to be pretty sure that this is pretty hot, or was collected at a pretty hot temperature. So the first thing I'm going to do is I'm going to go ahead and write down our temperature of 96.5 degrees Celsius. Now, the temperature you collected your first experiment, your first titration at, was, of course, 21.7 degrees. So we're much hotter now, and we're going to see how that affects our equilibrium. You're going to use these two KSP expressions we're going to come up with to solve for delta G's. All right? And once we know our delta G's and our temperatures, you're going to graph a line and come up with our delta H and our delta S, okay? We've kind of done this type of experiment before. We're gonna let this kind of cool to room temperature. It's pretty close. Our calcium hydroxide solution that was saturated when the temperature was 96.5 degrees Celsius. So now the question is going to be, do we have more or less OH sitting in here? All right, so we're going to make sure we get 10 milliliters just like we did before. It's nice and cool now. All right, well, one thing here, it's a little bit of a problem, and I don't want to do it over again. It's okay, right? But the volume that we collected is a little bit less than 10, unfortunately. We've got what looks like about 9.2 milliliters in here. So we're going to make a quick change, right? Instead of that, we have 0.092 liters, right, collected, and the experiment should work just fine. No issues here. It's just we're gonna take a little bit less base to neutralize, okay? So we're gonna do this, all right? And then, of course, we're gonna rinse. Make sure we get all of that hydroxide that we can. There's one. There's two. And there's 3 rinses. All right. A couple drops of bromothiol blue. There we go. Got that in there. I'll move this over to the side so you guys can see. All right, now it's time to begin our titration experiment. We're up here at about 0.7. Make sure that's right. Yep. Let's see, 0.5 is there. No. I think we're more like about 0.6. It looks like about 0.6 milliliters is where we're starting at. 0.6. We're going to have to see what we get to as we neutralize this. And we're going to start adding this slowly here. All right. So there we go. We're going to just kind of continue to do this slowly. And I'll probably fast forward this part of the video so you guys don't have to sit here. All right, there we go. Much less this time. And I gotta get up here to look at it. It doesn't even look like we got down to 12. It looks to me like we're at 11.8. 11.8 milliliters. Right? So the total volume that we used here was 11.2 milliliters, which we're not going to use. We're going to use it in liters like this. Okay? We're going to multiply those two numbers to get our number of moles. 0.0112 times 0.01, and we get this number here. 1.12 times 10 to the negative 4th. Right? And since this is the equivalence point, it's also the number of moles of this. Now we can use these two numbers here, divide by 0.0092, and we get this number here, 0.012 molar, which is about half of what we calculated before. Okay, so you can see here that equilibrium should be shifting to the left, to the reactant side, because we're making less hydroxide at these high temperatures. So you're going to find the KSP at both temperatures, and then you're going to find delta G at both temperatures by using the formula, and then you're going to graph this expression here. Delta G is equal to delta H minus T delta S. You can rearrange this into the shape, into the equation of a line that looks something like this. Delta G is equal to negative T times delta S plus delta H. Hopefully you see here. It's our equation for our line. We can even flip-flop these around like this. delta S and T, right? And now this is Y, this is M, this is X, and this is B right here. Okay, so that's going to be your equation for your line. Make sure you've got your temperatures in kelvins here, and make sure you've got your delta G's in kilojoules per mole, and that will be what these other numbers come out at. Okay? All right, good luck, and I'm around if you have questions.